Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in. Okay, so picture this. March 2026. Claude, a leading AI platform, goes down. Not because the fancy AI models broke, not because the GPUs melted, but because people couldn't log in.
Right? The report is pretty clear. The core AI was humming along without issue, to quote Yadav's analysis. The problem was the digital front door. It's like buying a supercar and then realizing the garage door opener uses two D-cell batteries from 1998.
Exactly. And this wasn't just a hiccup. The analysis calls it a slow-motion failure. The first incident, on March 2nd, was a control plane failure. Authentication services overwhelmed, users locked out. The AI is still doing its thing, but nobody can get to it.
It's the ultimate if a tree falls in the forest scenario for AI. If Claude generates the perfect haiku, but no one can log in to read it, did it really happen? This highlights a critical bottleneck in what the report calls non-AI components.
So let's dig into that March 2nd incident. The report says initial signs of trouble weren't bad AI responses, but rather widespread login failures, timeouts, authentication errors. What was the trigger for all this, according to Yadav's breakdown?
The analysis points to a massive, unanticipated surge in new user signups. Apparently, a new, highly publicized integration with a popular productivity suite dropped, and everyone wanted in. So, not malicious, just too popular too fast.
Which makes total sense. We've all seen that happen. But the report goes on to say that the services responsible for creating new user accounts, generating UUIDs, hashing passwords, writing to a central user database, they just weren't ready for that load.
And that's where the classic bottleneck scenario comes in. The report explains that in distributed systems, your overall throughput is limited by your slowest component. Here, the authentication service became that component. Imagine a single turnstile trying to let a stadium full of people in right before kickoff.
So legitimate login requests from existing users were stuck behind this flood of new sign-up requests. It wasn't that the AI couldn't handle the queries, it's that the system couldn't figure out who you were or if you were allowed to ask them.
Precisely. It was a failure of access management, not a failure of intelligence. That's a profound point, isn't it? We spend billions on GPU clusters and model research, but if the foundational pieces can't keep up, it's all for naught. This is the kind of stuff that keeps engineers up at night.
It really is. It's the unsexy but critical stuff. The report then makes a key distinction between the inference plane, the glamorous part with the GPUs and models, and the control plane, which is basically everything else that enables access.
And that everything else is extensive. We're talking authentication, authorization, user provisioning, rate limiting, API key management, routing, load balancing, billing. It's the nervous system that directs traffic to the brain.
Yadav's analysis claims that Claude's control plane, while functional normally, was unprepared for hypergrowth. And the report notes something important. Control plane services are often harder to scale than stateless data plane services. Why is that?
Because they're frequently stateful. They deal with user sessions, database transactions. These require strict consistency, making simple horizontal scaling a much more complex dance. You can't just spin up 100 new authentication servers without thinking about how they'll all talk to the same user database or how to handle concurrent writes for new users.
So the potential architectural flaws the report highlights really resonate with that. First, a monolithic user service. If one part of it, like create user, gets overwhelmed, it starves resources for something else, like validate login.
A classic. Imagine a single microservice that's suddenly not so micro, and one function brings the whole thing down. Then there's the synchronous dependencies. The sign-up process probably involved a chain of calls: create user, provision API key, update billing. If any one of those downstream services slowed down, it would cause a cascading failure, holding up resources upstream.
That's the distributed systems nightmare, isn't it? One slow call turns into a backlog, then a timeout, then a total outage for that chain of requests. And the third point the report makes is probably the most painful: under-provisioned, boring infrastructure.
Oof, yeah. Underinvestment in these less sexy components. billions for GPUs, but maybe not enough for the team building and scaling the auth system. It makes you wonder, did Anthropic's team perform adequate load testing on their sign-up flow, or was all the focus on testing the inference layer's tokens per second? That's a gut punch for any engineering manager.
It's a common pitfall, though, especially in fast-growing companies. Everyone wants to build the next cool feature, not necessarily shore up the foundations. It's like gaming launch days, where login servers melt down while the actual game servers have capacity. It's the same story.
The conclusion here is stark. A system is only as scalable as its most constrained component. And on March 2nd, that component was the control plane.
All right, if the March 2nd incident was a warning shot, the report makes it clear that the March 11th outage was a direct hit. This was deeper, more widespread, and longer lasting.
Oh yeah, the entire platform was unavailable. API returning 500 errors, website down, even existing sessions got disconnected. This wasn't just a gate problem. It was like the entire city went dark.
And the root cause, according to Yadav's analysis, was a primary application database suffering from critical I/O performance degradation. That sounds like a fancy way of saying the database was choking.
It does, but it's important to deconstruct it. Primary application database implies a single logical database, even if it was a cluster. But it was acting as the single source of truth for many services: user sessions, API keys, and conversation metadata. This database was the heart of the operation.
And deteriorated I/O means its ability to read and write data became critically slow. The report suggests a few reasons why this might happen.
Right. Could be hitting the provisioned IOPS ceiling in a cloud environment. You pay for a certain number of input operations per second, and if demand goes past that, the provider throttles you. Or a noisy neighbor, if it's on shared infrastructure, another application hogging resources.
Or even just inefficient queries, right? One bad join or full table scan on a massive table, and suddenly the database is spending all its time sifting through data instead of serving requests.
Exactly. Or, worst case, a hardware-level issue with the underlying storage. Whatever the cause, the effect was devastating because of what the report calls a massive blast radius.
This is where the centralization really bites you. When that database faltered, it didn't just slow down one service, it took down the API gateway, the web front end, the login service, even the inference layer eventually got impacted, trying to retrieve user context.
It's a textbook example of an architectural anti-pattern. By making one database a shared dependency for everything, the entire system's reliability became tied to that one component. A failure in the database was functionally equivalent to a failure of the entire platform. It's like the 2021 Facebook outage, where a single BGP configuration error made their own DNS unreachable, bringing everything down.
That's a great real-world analogy. It's the same core problem, a single centralized point of failure bringing down a global service.
Now, amid all this architectural critique, Yadav's analysis does highlight one crucial design choice that actually prevented things from being even worse.
The architectural separation of the control plane from the inference plane. The report mentions that during the March 2nd outage, some users who were already logged in could still use Claude.
Yes, and API users with valid cached API keys could still send requests. This means the core AI, those GPU clusters, were actually operating independently. They weren't calling the authentication service for every single request. That's good design.
So what did that decoupling achieve, if anything?
It prevented a total system meltdown. The core, expensive, resource-intensive part of the platform kept functioning. The failure was contained, at least somewhat, to the management and access layer. This shows a degree of architectural maturity. They likely used short-lived signed tokens like JWTs or cached permissions to achieve that separation.
But the report quickly follows up by saying that this decoupling, while positive, was ultimately insufficient. A running engine is useless if the doors to the car are welded shut.
Which is spot on. For the vast majority of users, it was still a total outage. The ability for a small subset of existing sessions to continue operating was a minor consolation. It raises that key architectural debate. Is simple control data plane separation enough?
And the March 11th outage answered that with a resounding no. When the centralized database failed, it took down components of both planes that relied on it for state.
Exactly. The report suggests that while the logical separation existed, they shared a critical piece of stateful infrastructure, which essentially negated many of the benefits. The concept was good, but the implementation had a crucial flaw. This is where a more advanced, more truly isolated architecture would come in.
Like AWS does with its regions and availability zones?
Even more granular than that. True isolation would involve partitioning the entire infrastructure stack, control plane, database, inference layer, into multiple, fully independent units. A failure in one unit affects only the users within it, not the whole system. That's true isolation. That's the next level of resilience.
So these fictional Claude outages, as deconstructed by Yadav, offer some serious real-world lessons, even if they didn't actually happen. What are the big takeaways for you?
The first one the report highlights is critical. AI reliability is foundational, not just model deep. We're all focused on model accuracy, tokens per second, cutting-edge research, but these incidents show that the mundane infrastructure, auth services, databases, load balancers, that's the bedrock. An S-tier model on C-tier infrastructure gives you a C-tier user experience every time.
That's a brutal but fair assessment. And the second lesson ties directly into the March 11th outage, the perils of centralized state.
Absolutely. It's a textbook case study on why putting all your eggs in one basket, especially a database basket, creates a massive blast radius. Modern systems aggressively partition state using various distributed approaches. The goal is to ensure a single component failure doesn't take down the entire system.
And then there's the uncomfortable truth. Boring infrastructure requires A-list engineering.
Oof, this one hits home. Building a globally scalable, resilient, secure authentication system is a massive engineering challenge. It needs top talent, resources, and rigorous testing. Companies that treat this infrastructure as a solved problem or an afterthought are doing so at their peril, and we saw that peril play out.
And the final lesson from the report, a slow-motion failure reveals systemic issues, really brings it all together. The first outage was a clear signal, but the underlying architectural weakness wasn't addressed, leading to the second, more severe one.
It's about deep, systemic postmortems, right? Not just fixing the immediate trigger, but asking why the conditions for failure existed in the first place. These kinds of failures aren't one-offs. They're symptoms of deeper architectural debt or misprioritization.
It really makes you think about how we build these complex systems. It raises some thought-provoking questions, too. As businesses build on top of these platforms, will we see SLAs that are as rigorous as those from AWS or Azure?
And how will AI infrastructure design evolve? Will we see more AI-native architectural patterns that prioritize resilience and graceful degradation from the get-go? Because right now, it seems like we're still often applying traditional distributed systems patterns, sometimes with glaring omissions.
And finally, the role of public accountability. The value of an independent analysis like Yadav's is clear. Will the industry embrace transparent, detailed public postmortems to foster collective learning, or will failures just be hidden behind vague status page updates? It's a critical question as AI becomes even more intertwined with our lives.
Ultimately, these fictional outages serve as a powerful reminder. AI's success isn't just about brilliant models. It's about the strength and resilience of the infrastructure holding it all up. The ghost in the machine isn't the AI, it's the database I/O.
Ship it carefully.